Okay, so last week we just wanted to see how we can use the simulation environment, to run this particular kind of simulation. Okay, so the example that we have, we're told that ammonia is produced from the Haber-Bosch process by reacting nitrogen gas with hydrogen in a 1:3 ratio. However, since nitrogen is obtained from air, it always contains 0.5 mole percent of argon. The reaction occurs at 200 bar and 400 degrees Celsius. Our suppliers are able to deliver the feed at the required pressure, but at room temperature due to the cost and dangers of transporting a high temperature gas. The process has a single pass conversion of 33%, hence the products must be separated and recycled. And we achieve this by cooling the product and then separating the ammonia. We said that, however, due to the presence of the impurity, a paired stream is taken before recycling the unreacted feed. Simulate this process for 100 kilomole per hour of nitrogen feed. And we are told that the temperature at the cooler is to be determined iteratively. We want to recover all the ammonia in the gas stream leaving the reactor. So for the sake of those who were not here last week, I would recap a few things. This was a simulation that we started last week, and we said that we are reacting nitrogen and hydrogen to form ammonia. So we know the process. You react nitrogen and hydrogen to form ammonia. And the question told us that the feed is coming in at the required pressure, but then not the required temperature. So we'll have to heat it. And I mentioned that when it comes to the main simulation interface, there are two main things that we have to specify. So we have the streams and then we have the blocks. The streams are the things that are responsible for the flow of material. So if I have hydrogen flowing, I have nitrogen flowing, we would have a stream to represent them. If I have any compound or any material or any chemical that is flowing through our system, we can have a stream. And I also mentioned that aside just the material streams, we can use heat streams, work streams, power streams. But in these applications, we can look at them later. For introductory simulations, we just work with material streams. And I also mentioned that we have different blocks. So the blocks are the different unit operations we know. We have heaters, we have reactors, we have different types of separators, flash columns, distillation columns, all these things. We have valves, pumps, compressors. So we have all these different kinds of unit operations available. So that those are the ones that we refer to as the blocks in Aspen. And the streams and the blocks can all be found under what we call the model palette. So that's what we see at the bottom over here, the model palette. So if I want to work with a particular kind of block, maybe I want to deal with a separator, maybe a flash column or a decanter, I can select the specific kind of unit that I need for my simulation. So what we started with was that we wanted to mix the hydrogen and nitrogen first. So this unit here is a mixer, right? Then after we mixed them, we heated them to the required temperature, because if you are supposed to feed in your material into a reactive system, you wouldn't just feed it in at the wrong temperature. The feed temperature matters. So we have to feed this in at the required temperature given to us, and then we can perform the reaction. So that was the first part of the simulation that we did, right? But let me see. For those who were not here last week, were we here last 2 weeks? I need to know so that I know if we are familiar with how we specify the properties. Because we'll be around last 2 weeks. Okay, so
Yes, please.
okay, and that's fine. That's fine then. Sure. So when we put the streams and then the blocks together, to specify them, you double click on it. So for hydrogen, for example, if I should double click on this stream, I have the inlet temperature. Sorry, I have the stream temperature and pressure, and I have the flow rate, and then I have the composition. So I use mole fraction, and then I put in the values, right? So you can work based on the units that you want, or the kind of base, whether you want to work in moles or mass flow. You can choose any of those ones. So that's for the stream. For the blocks, you double click on them as well, and you can choose temperature and pressure. Some of them you can decide to choose something else, maybe pressure and vapor fraction. You can do all of those things. And one key thing I mentioned last week was the fact that for a lot of these blocks, you need to pay attention to the valid phases as well. For our system, we can expect some amount of liquid to form at a point, can expect some amount of vapor to be present. So we can keep the valid phases under vapor liquid. But then there are times that you may have to specify it as just vapor, right? Especially when it comes to units like the compressors and turbines. So that's just one of the things to keep in mind. Okay. After we specify the heater, we came to the reactor itself. So just like the heater, we'll start with the temperature and then the pressure, and then we'll now add the reaction. So we clicked on new, and when we did, it brought us to this interface. So we had the reactants, we had the products, and then we had their stoichiometric coefficients. The negative is just because it's a reactant, right? Oh, sorry, this is -3. Yes, okay. And then we use the conversion, the fractional conversion, because the question told us that we have a single pass conversion of 33%. So that was here. So our fractional conversion is 33%. So if we have all of these things down, we can now continue from there. So I'll just reset it and then I would run the simulation one more time. And please, that's also another very important part of our Aspen simulation. Sometimes when you run a simulation, especially if it's a very large simulation, Aspen stores some of the data. So it might keep some values, right? If you want to rerun the whole simulation, maybe you made a very significant change, it's advisable that you reset it before you run again. If the change is not so significant, if it doesn't have maybe a lot of recycle loops or it's not a very complex plant, you can just run it normally. But then one of the things I really like to do is to always reset before I run. So for if you want to reset, you can come to the very top here where we see the name trial example one. And then we'll move towards the left. This button up here, that's the reset button. So you can just click on OK. So it purges everything and then we can run the simulation. Okay, so it's taking some time to run, but it will come soon. Okay, this is taking quite some time. Anyway, while we wait for it to run, the next thing we have to do is that the question said we want to recover all the ammonia and then we want to recycle the unreacted feed. So it means that there has to be some kind of separation, right? So our products here would contain ammonia. Some ammonia will be formed. Okay, our results are available, so we can look at them. So we said to check results, we can right click on the block order stream and click on either results or stream results. So click on stream results because we want the data for the streams. This was the inlet to the reactor. This was the outlet from the reactor. So let's look at the ammonia that was formed. So if we click on mole flows, we started with 0 kilomole per hour of ammonia. That was what was coming in. And now we have 65.67 kilomoles of ammonia coming out, right? The argon did not react, it's inert. The hydrogen, it will reduce because it's definitely going to take part in the reaction. Same thing with the nitrogen, right? So we want to now separate this ammonia from the rest of the feed, the unreacted feed. And then we want to send that unreacted feed back as a recycle. So the first thing we have to look at is how do we do the separation? And the second thing is how do we do the recycle? That's going to be the focus for today. For the separation, we'll first have to cool it. So one thing I would show us is you'd realize that when we check the stream results, we had all the data for the different streams. We had the temperature, we had the pressure. So we have those values. We have the temperatures, we have the pressures, we have mole fractions, we have all these values. But sometimes you may not want to always come back to be checking the stream results. It will be helpful if you could see everything at once, right? So one of the things you can do is that all the tabs up here, we see home, economics, batch, dynamics. You come to modify. When you come to modify, you see over here stream results. So we see the different ribbons, flow sheets, unit operation, stream results. You can come to stream results and then check temperature, check pressure. So now it shows us the temperature and then the pressure, right? And we have the key here. So the ones that are a little bit more circular are the ones that are for temperature. And then this other one here is going to be for the pressure, right? I think that's the hexagonal shape. That will be for the pressure. So we can see that it was coming in at 400 degrees Celsius, 200 bar. It's coming out at 400 degrees Celsius, 200 bar, right? And we know that it's going to be vapor. So you can even decide to add vapor fraction to it. So we see that everything is vapor. If we want to separate it, we may have to cool it, or we will have to cool it down so that the ammonia can become liquid. Then we can separate the vapors from the liquid. Please, I hope that's fine. I hope you're all here up to this point. Is anyone lost? Please, are we all here up to this point?
Yeah, we are doing fine.
Okay, so that's fine. So we would try to cool it first before we do the separation. So you're going to add a heater block. So even though it's a heater, we see the word heater. This unit is actually used for both heating and cooling. It's just a temperature change block, right? So we'll place it down. And once again, we see that the cursor is a crossbar. If you continue to click, it will place more of the units down. So to avoid that, you click escape on your keyboard. So now we can join this stream, we can connect it. And once again, if you remember, I mentioned that there are two ways we can connect the stream. So you can double click on the end of the arrow and then connect it to that inlet, or you can right click on the stream, click on reconnect, and then maybe destination or source. So this one we are reconnecting it to the destination where it is going to. So I can join that here, and then the outlets would be this. So the question didn't tell us what the outlet temperature for the cooler would be. But the question said that it has to be determined iteratively, right? So we want to recover all the ammonia and we have to determine it iteratively. So the temperature of the cooler has to be determined iteratively. So there are a number of things we can do in Aspen to make it easier for us. We have different blocks that can make it easier for us. Some blocks will just do the iteration for you and pick the temperature that would work best, right? But we'll come across them in the course of time. They are usually under the manipulators tab. So we use certain blocks here to do that, especially the design spec and then the calculator block. They are very, very efficient for those things. So it will be part of the things that we'll talk about in subsequent discussions. But for now, let's say that we don't know much about them. So what we can do is that we can double click on the heater or the cooler. The pressure is supposed to be 200, but that one isn't changing. And you can guess the temperature. So let's say 100 degrees Celsius. So you are going to do this iteratively, and then you can now be checking how much ammonia has become liquid, how much is still vapor, and all of those things. So if I should run the simulation, it says results available, no errors. So let's check the stream results. I would right click, click on stream results, and we see that the phase, we still have vapor phase, vapor phase. So we know that everything is still a vapor. We don't have any liquid formed yet. So we can come back to the heater. The heater is here. Let's drop the temperature to, let's say, is that the right heater? Sorry, 1 minute. No, no, so the heater is B1. Okay, so I almost specified the wrong heater. This was supposed to be 400. So the heater that we are specifying now is B1. So let's drop this, let's say 50 degrees Celsius, and let's run it. So we still have results available, no errors. We see the vapor fraction has changed, 0.96 now. And if we should check the results, we realize that for the inlet to the cooler, which is the outlet from the reactor, we have the phase to be vapor. But then over here, nothing is written here. If nothing is placed over here, it means it's a mixed phase stream. So it has different phases in there. So how can we tell how much is vapor, how much is liquid? When you scroll down, you would see vapor phase, you would see liquid phase over here. So if you should click on the the cross symbol, you can now get access to the information for the vapor phase, right? So you can check the mole flow, realize that we had 65.67 kilomole per hour of ammonia coming in as vapor, and 52.91 kilomole per hour of ammonia is still vapor. So it means the balance would be the liquid, right? For the nitrogen and hydrogen and argon, almost everything is still vapor. It's just a very, very small amount that became liquid. But then for the ammonia, we see about maybe almost 7 kilomole per hour became liquid. So we can click on liquid phase as well and then check the same thing. Oh, I said 7, eh? Oh yeah, it would be like almost Yes, it should be around 12. Sorry, my math failed me today. So that's what we'll be getting. So we see that some amount of ammonia has become liquid now, but then we still want all the ammonia to become liquid. So what I prefer to do, instead of me changing this temperature over and over again till I see the best value, what I normally do is that right from the beginning. So let me come here. I check the mole fractions for the total stream, not the vapor or the liquid, the total. So I would get rid of the vapor and liquid. And for the total, the mole flow, sorry, the mole fraction. So what I do is that I specify the vapor fraction in the heater. So I know that these are the things that are present in my stream. I want all of these ones to be liquid. So I want the nitrogen, hydrogen, and argon to be liquid. But then I want to be vapor, sorry, but I want the ammonia to be liquid. So if I specify the vapor fraction, it should be 1 minus the mole fraction of ammonia, right? Ammonia is liquid. So if I want the vapor fraction, it should be 1 minus that. And then I'll use that value as my vapor fraction. So if I should say 1 minus 0.19, that's 0.803577. So all that we are trying to say is that, okay, in my heater, instead of me changing the temperature consistently, I'll come to the vapor fraction. And then looking at the streams, if I should add this, and this, it should give me the ones I want to be vapor, the fraction that I expect to be vapor. You know that ammonia will condense before the rest of them. So we can specify all the others to be the vapor fraction. So that should be around 0.803. So if I should come back here, I can put in that value 0.803577, and then I can run the simulation. So results available, no errors. And if I should check it this time, if I should check the liquid phase, realize that most of the ammonia is now here, right? We started with about 65.67 kilomole per hour of ammonia. And in the liquid, we've been able to remove about 65.57. So that's very significant. Okay, so please, I hope we get the idea behind the vapor fraction, liquid fraction stuff. Please, do we get it?
Um, yeah, but can you go over again one more time?
Okay, so the idea behind it is that we have nitrogen, hydrogen, argon, and ammonia, right? So let me come back here, the original stream, before we looked at the liquid and vapor. So these were the mole fractions. So this was for nitrogen, hydrogen, argon, and ammonia. We are saying that we want all the ammonia to be condensed, or most of the ammonia to be condensed, and we want the others to be vapor so that we can recycle them. So instead of we changing the temperature consistently until we get all the ammonia condensed, what we can do is that we can specify the vapor fraction in the heater. So the vapor fraction, we are just saying that, okay, everything that is coming in, let this percentage of it be vapor, right? So how do we determine that percentage? We can take the mole fractions. If we sum up all these mole fractions, we'll get 1. So nitrogen, hydrogen, argon, ammonia will get 1. But we only want nitrogen, hydrogen, and then argon to be vapor, and we want the ammonia to be liquid. So we can just add the mole fractions for the ones we want to be vapor, and then specify that as the vapor fraction. Because in our system, we have about 0.199 of our stream to be ammonia, sorry, nitrogen, 0.602 to be hydrogen, 0.00149 to be argon, right? So those are the mole fractions. If we add everything together, we would have the total vapor mole fraction that we want, the ones we want to be vapor. So that becomes the vapor fraction. And then we can feed that value into the heater, and then we should be good to go. Or you can make it 1 minus the one that you want to be liquid. Please, I hope that's okay.
Yeah, that's fine. So with that, the we don't have to worry about the heating temperature in the.
Yes, yes. It will determine
Okay,
that
it
for
will
you.
calculate itself.
Yes. But
Okay,
then
okay.
the thing about this is it doesn't work in every case. Over here it works because ammonia is more condensable than the others. So it will take a lot to condense nitrogen, hydrogen. I don't even know. I know hydrogen is not even condensable. So it will take a lot to condense something like nitrogen. You will need probably extremely low temperatures, maybe cryogenic temperatures, to do that kind of condensation.
Yeah,
So this works because ammonia is easier to condense as compared to the others. But if you had a case where there was another substance that was more condensable than ammonia, that one would condense before ammonia. So Usually for those ones, you may have to use a different method, like the other blocks I spoke about. We'll talk about those ones in subsequent discussions, not for today. But you may have to use a
Oh,
different method. Otherwise, it becomes a bit more complicated to figure it out. Okay.
okay.
So now that we've done that, we can see that the temperature is minus 93. So imagine you trying to do it iteratively. You started at 100, you went to 50, you went to 20, you went to 10, you went to 5, then you now go to negative 20. It becomes it becomes a bit of a challenge, right? So in order to avoid all of that, you can just use the method I showed us. So I just got prompted that we have about 10 minutes. We can do something significant before the time beats us. If we don't finish, we'll just rejoin the meeting. So we are done with the heater. Let me take this out so that it doesn't look too messed up. The next thing we want to do is to separate the vapors from the liquid. So we'll come to separators. Now we'll choose a flash column. We don't need a complex separation method for this. So we'll connect the stream and then we have to get two outlets. So remember the red arrows are compulsory. So we need a vapor outlet. We need a liquid outlet. So we can label them as vapor and liquid. So vapor and then liquid. So we double click on the flash and the temperature. We can just pick the temperature that we got from here, or we can do the exact same thing we did for the heater. So the pressure was 200 bar. The vapor fraction was 0.80803577. Right. So if we run, results available, no errors. And for the vapor fraction, if you make the mistake of um, sometimes if you don't use the right value, you may get some errors. So if I made this 0.80, let me do it in the heater. It will give us an error because it's like we are trying to force um more of it to become liquid and it doesn't easily become liquid. The other gases, they are not condensable. So it gives us an error, right? So you'll be seeing errors like this flash calculations failed. It wasn't able to perform the flash calculations because we gave it the value we gave it was too low. We are trying to force some things that can't easily become liquid to become liquid. Okay, so that's just by the way. So our results are available. Now we can check the stream results here, and then we can see our separation. So liquid phase, vapor phase, this is the mixed phase coming in. So if we check the mole flows, this was the ammonia coming in. This is what is coming in as the liquid. This was coming out as vapor. So we have most of the ammonia in the liquid. And then for the others, we have most of them in the vapor phase. So what we have is good enough. So now for the recycle, we may be tempted to just take this stream and bring it all the way back to the feed where we did the mixing. But then one thing about Aspen is that if you should do this, Aspen would always have errors. Aspen struggles with recycle streams. So it would always give you an error, right? It's like the material is going to continue to build up in the system and Aspen is going to struggle to let it converge. So you see things like solver O1 error. So it's not able to converge, right? So these are some of the things. So how do we handle recycle streams? For us to handle recycle streams, we need to use or we need to include a purge stream. So we all know what a purge stream is, right? From chemical process calculations. Please, are we all familiar with what a purge is? Okay. So if we are talking about a
Yeah.
purge stream, okay. We are talking about a pair stream. We are saying that we would remove or we have a stream that would remove some amount of the material from the main stream that we have. Instead of sending everything back, we'll just remove some amount of it and then we can maybe flare it, send it to a different section, anything of that sort. So because we want to split the stream, we'll come to mixers or splitters and then we'll choose F split. That's the splitter block. We've used a mixer block before, we'll use a splitter block. So I'll place this block down. And if I should try to join it, realize that the inlet is at the back here, right? So for those who are worried about how it looks, the appearance and all of that, you may want to reorient this. So you can just click on this block, right click, click on rotate icon, and then you can flip it horizontally so that it just turns the other way. So that it looks a little bit neater. Then we can now have our recycle, and then we can have our page. So I'll label them. This will be recycle, but then this will be page. So I'll double click on the splitter and we have to get the split fraction. So how much, um, what fraction of the inlet stream are we splitting to the recycle? How much are we splitting to the page? So since we have just two streams, if we specify one, the other is implied. If I specify 0.6 for the recycle, it means the page is 0.4 because they have to sum up to 1, right? So if I should run this, we are getting errors. So this is another challenge because sometimes you may not know the split fraction that would give you um satisfactory results. So this is also another case where you may have to iterate quite a lot. So this isn't working either. So we can try, if we try something like 0.3 for the recycle, this time our results are available. We don't have any errors, right? So this is these are some of the things that we can do. Another very smart thing you can also consider is the fact that if you're looking at this from a very analytical chemical engineering point of view, it wouldn't be advisable to send this stream back and mix it with this stream. Can anyone tell me why? Looking at the temperatures and the pressures, can anyone tell me why? We have about 4 more minutes or so. Let's really try to finish this up so that we know that we are done with today's discussion. Does anyone have any idea why this may not be the best option to just send it back as it is? So realize that the inlet is coming in at 25 degrees Celsius and the recycle is at minus 103. So doing something like this can introduce thermal shock. We all know what thermal shock is, right? The temperatures are so far apart, it can cause thermal shock and it can damage our equipment. So you may decide to include maybe a heater here, heat it to 25 degrees before you send it back. So these are some of the things you can do, right? The more you are conversant with the principles of chemical engineering, the better the outcome of your simulations. So Aspen can give you some results, but at the end of the day, the value is in the fact that you understand what you are doing. So I'm just going to add a heater block, and then I'll connect it here, and I'll heat it to 25 degrees Celsius before the split happens. So this should be 25, and this should be 200 bar. So we may even have to change the split fraction. It's possible, right? But I think everything is fine now. And this makes a lot more sense. So please, I hope this is okay.
Yeah, we
Yes,
are
please.
following now.
Okay, so we have about 2 minutes and 40 seconds. Are there any questions? I'll save this simulation and I'll send it to us. But are there any questions? Okay. So if there are no questions, what we'll do is that next week, so today we're just trying to finish up what we started last week. So next week, what we are going to do is that I'm going to take us through some very specific things we can do in Aspen. So Aspen for thermodynamics, Aspen for chemical process calculation, Aspen for heat exchanger design. We'll have time to look at designing distillation columns in Aspen. When we are done with all of that, as I was telling, I think it was Pepra the last time, we would go into some very specific stuff. So maybe if we want to learn how to use Aspen for polymer synthesis, we want to use Aspen for maybe economic analysis, you want to use it to do optimization. We'll look at how we can do all those things too. So it depends on what our general interest would be. But then for the basic chemical engineering principles, we'll touch on all of them. Okay, so we'll end here for today. If there are no more questions, then I think that's fine. Yeah, I think I've touched on all the relevant things we need. Okay, so if there are no more questions, then I think that's fine. Okay, sure.
Okay, thank you.
You're welcome. Thank you for your time. See you next week.
All right, thank you very much.
Thank you. So I'll send the simulation to all of us right after this. Thank you. Bye.
Yes, please. Thank you very much.
You're welcome.